And the final speaker for tonight will be Alan Rush. Alan, if I may introduce you quickly. Alan is a fellow at AMD, and he's an expert in the deep learning and imaging with a whole bunch of experience in a variety of leadership positions in startups and other companies. So if I may, please come to the stage and enlighten us as the last speaker. So.
Yeah, thank you. All right. So I'm the last speaker for tonight. That comes with some responsibilities and in some cases a lot of fun. But before I start, I want to say that I could actually jump to my last slide because both Amir and Dr. Alexic covered just about everything I was going to say. So if we could, I need a clicker. Where's the clicker? Here's the clicker. So I'll jump to the last slide and then we can all go home. So I'm going to talk about deep learning challenges, particularly for scalable, high performance computing, and what are the computational requirements, and what are we looking for, and how do we solve them. More or less at the data center area, but as we've found now, there's lots of places where deep learning is used in both training and inference that require all sorts of different types of calculations and performance. So a lot of what we cover in looking at deep learning and high performance types of calculations in the data center somehow translate into lower level areas and applications as well. So let's see, is this thing working? There we go. No, good. So I'm going to cover 4 or 5 different topics. We've already seen a lot of information about the emergence of deep learning, and it turns out it has a very interesting history, so I'll put a different type of spin on it. And the major application focus for which we see lots of examples where deep learning can actually help. And what are the drivers? Why is it important to design hardware and software that matches the requirements for deep learning? And then the flip side, what are the things that are happening to make these calculations either better, easier, faster, and what is changing in terms of the algorithms that are being developed? It turns out that one of the assumptions that we make about primitives and building blocks and so forth is that they're immutable. They don't change. We don't think that there's going to be a huge change in the way the basic building blocks are done. Now, if that happens to be not true, we have some more work ahead of us. I'll touch briefly on training and inference. It's already been covered quite a bit, but obviously there's a big difference between what we do in the training set activities versus what we do in the inference. We'll talk a little bit, and this may be repetitive because, as I said, there's already been quite a bit of talk about what are the techniques for accelerating things, about approximating things, and about optimizing things. So we'll talk a little bit about that, and then finally some thoughts about going forward. So another way to look at the history here is taken from a Gartner hype cycle. This is a very widely used theory that is taught in MBA schools of all places, where if you have some ideas and you get a whole bunch of people excited about it in the beginning, and you say it can solve everything, it can do everything, it costs nothing, only to find out that all of that's not true. It can't do very much of anything, it costs a whole lot, and nobody knows what to do with it. So this is kind of what happened in the 80s and 90s. If some of you were around, I remember it very well. We used to call it fuzzy logic and all sorts of fancy names, and people thought, wow, this is really cool. AI is going to solve everything for us. Only to find out that it didn't work, it was too expensive, and nobody knew what they were doing. So there were some really good guys, though, that kept moving and kept saying, no, this will work, and we will make progress. And as mentioned by Amir, LeCun and Hinton and others were just persistent. They said, no, this will work. And then finally, a few years ago, the convergence of big data, large training set databases, powerful enough machines, and enough memory to actually do all this stuff was sort of the door that opened and a lot of this became actually useful. So now we have DNNs, CNNs, deep belief networks, RNNs, and so forth. All of that was actually started a long time before, but as the facilitating parts became actually useful, that's where things started to unravel pretty quickly. And there's a quote by Donald Rumsfeld that I like a lot because it sort of reminds me of the state of affairs that we're in. It says something like, there are things that we know. There are things that we know we don't know. And then there are also unknown unknowns, and these are things that we don't know that we don't know. So we are more or less in that state right now. We know some things work, we know some things don't work, and we know why, but we also know that there's a whole bunch of stuff that we don't know, and we have to figure out how to know that. So that's our job, and that's, as we go forward in this, it's not just about algorithms and ways to do stuff, hardware, software, and so forth. It's figuring out, as Jeff Hinton says, what is really AI? It's not the way we have it today, but it's like what we would like to see it. And that's our job of where we are. So on the Gartner curve, we are kind of on the upswing. We're kind of in year 5 of the maturity part. And this is where we feel like lots of progress is being made and lots of expectations. And the problem with these kinds of issues is that there's a lot of hype and there's a lot of expectations. What leads us, though, is that everybody knows that if you had AI, things would be really great. And so the original title of this slide was that there's a demand for machine learning and the demand for solutions. I modified it to say that there's pent-up demand, because if we had AI 20 years ago, life would be a lot different today. And what this amounts to is that this is something that everybody's been looking for a long, long time. Whether or not we get there today or tomorrow or the next 5 years or so is really a function of how well we, we do our job and apply these principles to these various applications. And that can be described in all sorts of ways. There's lots of papers being written. You can pick and choose the different category, the different way in which you look at this stuff, and the way in which these different algorithms apply. Some of them work really well. We know about image classification. We know about speech recognition. Some of them don't work at all yet. And the expectation is that over time, very quickly, hopefully, some of these will start to appear. And this translates then into a huge demand for more, better compute, more memory. Every imaginable way in which you can describe the metric, that's what we need more of. One of the reasons why is that while all of this stuff is great, we can do lots of stuff with big data, with lots of compute power, it's also enormously inefficient. And I've got some examples of that a little bit later. So historically, you had the data center, you've got some edge devices, and you've got ways to calculate lots of interesting things in the data center. But this is a very, largely asymmetric and unbalanced type of system. It worked well until things started to get pretty big in terms of the amount of data, the amount of information that needed to be processed, and where the users stood in the stack. More and more, we're starting to see intermediate heterogeneous processing, at the edge, like we heard earlier from Qualcomm. And the amount of information that's processed and managed throughout this stack is actually starting to change pretty radically. So we call this the sort of big data disruption. This probably is a little bit more dramatic than it needs to be, but the point is that we are in an age where the amount of data is now sufficient, and we'll have a slide that shows a little bit why that is. And the amount of information that we have is becoming sufficient. And now it's the job of us to figure out how to compute all that stuff. 2.5 quintillion bytes of data generated every day. It's hard to imagine what that means. I can't put my arms around it. We think of tweets as 140 characters. Well, if you generate 500 million of them, that's a lot of data. An hour of video data uploaded every second, and so forth and so on. So the amount of data here is clearly way, way more than historically we've been able to deal with. So earlier on in the 60s, we had mainframes, and everybody, typed away. In our case, we did IBM punch cards. That's, most of you don't remember that. But that was the way we did business. The amount of compute data impact was measured in the thousands. It was not very big at all. As we went through to the 70s and 80s, we emerged with the client-server kind of situation where there was a lot of compute done here and not much done there, and we got work done, but it was kind of messy. And then as cloud computing came on board, the amount of data compute impact was started to be measured in the millions and billions. And then finally, we're kind of at the point now where we call it the machine intelligence era, where the data compute impact is measured in the billions and trillions. So this is just to give you a sense of how much over time the amount of data, the amount of information that we have to manage, particularly as we enter into the machine intelligence era, is just overwhelming when you think about what happens in the data center. So how does AI play into all of this? And this is sort of a chart that I made that tried to encapsulate the idea that from humble beginnings, we've had a fairly, as Amir said, it's kind of gradual and so forth until just a few years ago. When LeCun did the handwriting recognition, everybody thought that was a great breakthrough, and then it was sort of an interesting application, became very useful, but today we look at that as a pretty small toy application. CNNs emerged with Krasinski as good basis for doing image recognition and classification. And this is the era that I like to call train to learn. So we're using machines, we're figuring out algorithms, we're figuring out how to train the machines to learn something. We're entering the day now, or entering the period now where lots of advances are being made, lots of improvements are being made, machines are getting bigger and stronger and more powerful, memory is getting much bigger, the capacity to do things is actually growing. And then future, we sort of get closer to that AI sort of definition, but more practically, I look at it as instead of training to learn, we're learning to train. And so that's kind of the difference in how I see the progression. So everybody's seen this. This is a training versus inference. You have lots and lots of examples. You want to train the network to do something. You haven't really necessarily told it what to do yet, but you said, here's a bunch of data, train yourself, give me, tell me when you're done. Typically that takes hours, days, sometimes a long, long time beyond that. And then for inference, you're saying, okay, here's an example, tell me what you see. And we expect that to take milliseconds, sometimes seconds, depending on the complexity of the network. Today, in a single GPU, you can expect to see the performance levels of that reach 10 to 15 teraflops. We've got a couple of products coming out which go into the 20, 25 teraflops. But that's the kind of performance and capacity that you would see typically today in neural networks. It's important to show how much progress has been made. We measure accuracy as a function of, well, how well did it do? I mean, compared to a human vision and human recall, how well did it do? Well, in 2012, when AlexNet came out, astonishingly, everybody thought 16.4% error was pretty good. Anybody who's ever done, image recall as a game or something like that would think, well, 16.4% is pretty bad. But in a span of 4 or 5 years, that number now is down around 3.5%. Actually, it's asymptotically pretty flat. We're not seeing much more beyond that. The fact is that that's actually better than human recall. So, pretty good stuff. This is a different twist on the picture that Amir showed, but it goes to show that the complexity of these networks is designed kind of ad hoc, sometimes by trial and error, but nonetheless to do much better job at extracting information from images. And the same theory applies to speech and natural language processing and so forth. We want to extract information from images, generate some feature maps and some intermediate levels of representation, and then train that to somehow give us a reasonable answer. One of the ways to understand that is to look at sort of a picture of what those feature maps are and what the filters do. And as you can see, in the beginning, things are rather abstract. They're looking for lines, they're looking for angles, they're looking for very, very simple patterns. In the mid-level, they're starting to amalgamate them into collections of patterns. And then finally, at the end, they're looking for real pieces of patterns that match more or less what the original image had. And this is, at a very, very high level, kind of a picture of how all of this stuff works, particularly in image type classification. Similar types of things are done for speech, although there's not a similar kind of representation visually that you can see. At the same time, the accuracy got better, so did the complexity got worse, if you want to think about it that way. The 2012 Krzyzewski paper described a 7-layer model, AlexNet, and it's the famous benchmark that almost everybody uses. But in very quick succession, we got GoogleNet, VGG, MSRA, and in 2015, the ResNet came out with 152 layers. So the idea of getting better results by adding more complexity and more layers has been something that's been followed now for the last several years. We're seeing examples now where there's some networks that are reaching 1,000 layers. So this is something that we know is anecdotally good. We don't know why it's good, but we know it works. Oops. So in the meantime, there's a lot of activity to say, well, let's be a little bit smarter about it, and let's generate different types of models. And this is just an example. There's a couple more, but I wanted to show you that it's just not about taking a one-dimensional view of things and say, let's just make these models more complex and see what we can find. A lot of experiments are now done with figuring out how to be a little bit more intelligent about what goes in the models and figuring out more efficient ways to get better answers. So this is an example called Mixture of Experts. The compute challenges are intuitively pretty simple. The more layers you have, the more neurons you have, the more connections you have, the more compute power you need. I mean, it's pretty simple. It doesn't get any more complex than that. I mean, there are fundamental calculations that are being done, but by and large, the bigger the model, the more connections, the more compute is going to be needed. If you look at just adding them all up, take a spreadsheet, somewhere in the neighborhood of several 100 million parameters, several billion to several 100 billion computations. That's kind of the order of some of these models. This isn't a complete picture by any means, but it gives you a sense that some of these complex models can add up from a computational perspective pretty quickly. One of the challenges that we have, though, is that while all of this is great, we can do pretty good stuff once we get the computation activity going, but it turns out that there's a relationship between what we call the arithmetic intensity, or the operational intensity and ratio of ops per byte, and bandwidth. And this is taken from the TPU paper, where some operations are compute bound. That's a good thing. You want your compute elements to be as busy as possible. But many models are not. They're bandwidth bound. And so the roofline model is a good way to abstractly understand where you are with respect to how these algorithms can map practically and to a theoretical extent on a system that you're designing. So looking forward in the network architecture space, this is a short list, but the point is that lots of people are now recognizing that, okay, this is great, I've got a model that works, that's fine. What can I do to improve the efficiency of it, how much space it takes up, what the computational impact is, and so forth. And so there's lots of work going on, and you know, probably half the papers that come out at NIPS and CVPR are all about figuring out ways to make this stuff more efficient. And so I've listed a few of them here. This is by no means exhaustive, but the point is that in some cases you can achieve a great deal of improvement at not much cost in terms of either lower accuracy or some other metric that you're using. And a lot of the activities here are aimed at making the networks more efficient at the expense of trying to find better ways to get more accuracy. This was, you know, covered earlier, and I'm not going to go through it, but the building block is the multi-layer perceptron. Almost every single model has this in one form or another. I saw one paper that listed them out as best they could, and there was probably 20 or 30 different variations on a theme. But the point is, this is the basic building block. In order to execute that building block, you have to do matrix multiply. And this, again, has been covered. We don't need to go through it. But the point is that understanding how even the basic algebra works and the basic, you know, primitives and the simple arithmetic is the basis around which we find ways to make this efficient for GPUs. So one of the ways to sort of envision all this and get an idea of what's going on is to look at the data and the weights as a set of tensors, n-dimensional, sometimes 4 or 5 dimensions, many times just 3, and then figuring out how they map properly or as best you can onto the resources that you have available. A GPU is generally a collection of very highly parallelized processing elements, and the trick to keeping a GPU busy is figuring out a way to map all of these elements nicely onto the array that you have available. And of course, these GPUs change in array size and different configurations, so there's no one-size-fits-all. You actually have to go through and figure out for each one what's the best strategy for mapping. Once you've got that, then from a data center point of view, we like to put GPUs together with CPUs. We'd like to put groups of CPUs together with groups of GPUs, and you can just imagine how all of this gets scaled out in a rather interesting way. And so for data center, challenges there are they have to compute a very, very large amount of training in a reasonable amount of time. And reasonable is defined differently depending on what customer you go to. But it's not necessarily as fast as you can go, but it has to be acceptable because there are limits to what you can do here. So for example, a high-end CPU, whether it's AMD or Intel, along with a set of GPUs in a rack filled with chassis of this stuff, has to run within a few kilowatts of power. So that means that you can't just add them all up, randomly put them together. You got to worry about what's the power allocation, what's the heating and cooling management, all sorts of things. So there are practical limits to all of this. But even beyond that, and if everybody understands Amdahl's law and so forth, there's a price to pay whenever you put more than one of these together in a chassis or on a network. And so that price is usually in the form of overhead communication, either by parameters or by data or however you want to do it. And so there's been a fair amount of work recently, and this is a paper that just came out a little while ago about how you can get near linear speed up, getting into the several hundred nodes of GPU. So there's a lot of work going on to try and factor these models in such a way that you can spread them out over a large number of GPU nodes and still get reasonably good performance. So lots of talk already on optimization techniques, pruning, compression, precision, fusion. There's a long list. And there's a lot of very smart people looking at this and trying to figure out mechanisms that make sense that we can use to optimize networks in the form of reducing the overall complexity. And so obviously if you have a fully connected network before pruning and then you have after pruning both on edges and in nodes, you can end up with a considerably simpler network. And of course, what we want to do is to do this without losing any accuracy. So all of these papers have as an exercise, okay, how much accuracy did you lose as a function of all of these techniques? And this is an area of some fairly serious ongoing research. So there's more complex versions of that, so you may not stop at just saying, well, I want pruning, or I want compression, or I want fusion. There's ways to combine them. And I think that, the work that Qualcomm is doing is exactly right, that, looking for the lowest possible profile that you can get for low power inference is going to be taking advantage of all of these types of techniques. In the same way, you can distribute data many different ways. We have data parallel, model parallel, and so forth. Plenty of really good papers describing the ways to do this to get optimal results. So I want to talk a little bit about, sort of the trade-off space between what happens when you try to apply all of these techniques to general purpose compute, GPU, FPGA, ASICs, and so forth. And it turns out this should be intuitively obvious that, the more general purpose you have a wider array of things that you can address, but you also have some limitations in terms of overall performance. Conversely, you can hit exactly what you need with a custom ASIC, but maybe you can't do much else, and that leads into the future-proofing because of what we have going on in terms of the evolution. So we have to be judicious about how we pick that. What we are looking at is a combination of things which gives us a better heterogeneous compute capability. HBM was mentioned earlier. We have several products which are currently shipping using HBM. It's a very efficient way to get memory in close to where the compute is being done. It's very efficient from a packaging point of view. It's very efficient from an electrical and performance point of view. So we're big believers in heterogeneous compute. We think that there's a role to play for all of the resources in a system, and we try to balance what those roles are, both from a hardware and from a software point of view. We recently announced and started shipping ROCm, which is our heterogeneous supported compute software environment. And this is the mechanism around which a lot of the optimization is being done to get our GPUs to a pretty high level of performance. Currently, we have 3 products that are specific for MI, although we have lots of other GPUs. The latest one that we just started shipping a couple of months ago is called MI25. It's actually in our Vega family. And it's got a 12.5 or so performance, teraflops of performance of FP32 and 25 teraflops of FP16. And it's quite well matched for these kinds of machine learning jobs. So the software architecture is really based on optimizing deep learning for a variety of different applications across the board, and then there's some interesting things that we're doing in the library layer, which I'll talk about. But the idea here is that all of the applications that we have, whether it's in cloud compute or financial services or even automotive, these are the common software attributes that we're looking for to support all of these applications. This is a little bit more detailed view of the stack. One of the things that is worth noting is that the support for frameworks, and Amir spent a fair amount of time talking about this. This is critically important. All of our customers are relying on these frameworks as mechanisms to do both the development and the deployment, primarily of the training types of applications. In deployed inference, it's a slightly different story. Some of these have relatively high overheads, so some of them are not necessarily applicable for real-time deployed environments. However, the development part of it definitely is. And then secondly, the middleware and libraries is the place where we put all of our middleware for optimization and mappings that I showed earlier about how you get the best performance based on the application and the model that you're trying to to develop for. And then finally, the promise of AI and machine learning is certainly here. The promise is here. The challenge is how to deliver really good solutions. And while some of these applications, the solutions are relatively well known, maturing pretty rapidly, others we have yet to see good proof points that they actually work. So this is a work in progress. I guess the message is, stay tuned, because we're going to be seeing lots of good progress. So finally, I close with, meet the challenge with a full toolbox. Machine learning is not an area where one size fits all or one chip can do all things. It's a combination of architectural, algorithm, technology, and good hardware and software products. So we aim to figure out the best way to address all of that. In our group, what we're doing is looking at advanced architectures to figure out how best to take advantage of the idea that sort of the Moore's Law plus is much more complex than the original Moore's Law, which we pretty much know is come to almost a screeching halt. So I think that's it, if there's any questions.
So, Alan, thank you very much for a very nice talk. Before we lose the audience, and before we go to the questions, let me ask Mujtaba to have some closing talks for tonight, and then we go to the questions, because how are we going to do this thing for tomorrow? If you can use that microphone. Alan,
You guys might leave.
for a second before.
Before you leave, we wanted to just make sure that we are on the same page for logistics for tomorrow. Please make sure to bring back your both badges for Intel Visitors Badge and also your conference badge. And please arrive around 2:15 p.m. to 2:30 p.m. because the venue is not available before that. And one other item is that we still have check-in desks available. So if you have your badge missing, or in case, or you didn't receive your gift bag or some items in your gift bag, like brochure or program and all that, so you could stop by tomorrow and pick it up from the team executive committee. And that's it. Then let's go to questions.
Questions, please.
So I had a question. Actually, I meant to ask a couple of the earlier speakers, but you guys have your own custom version of TensorFlow? Or are you taking graphs directly out of TensorFlow, or what?
So yeah, good question. So we actually just released TensorFlow, and it's now being distributed. It's pretty much the out-of-the-box TensorFlow. We've made connections to the various pieces of our own middleware, but from the application point of view, it's totally TensorFlow compatible as it sits out of the box. Yeah.
Excellent talk. It really summarizes a lot of concepts. I'm still a beginner in this field. So my question here is, we have become aware that cloud computing has now been called hierarchical cloud computing, with cloud, fog, and dew.
Yeah.
I don't know when it'll become sweat as the fourth level. But, joke aside.
Yeah.
Will you, what you meaning AMD, produce chips that will be customized for fog from performance point of view and from everything else point of view, and the custom chip for the edge that's called the DO?
Yeah.
You will.
So obviously, I can't talk about things that might be on the roadmap, but in principle, we have a division, it's called SCBU, that does exactly that. So it takes elements of our IP that we use in our standard products, and when the business model is right, we can make arrangements to create customized versions of that. So we already have that model. And there's no reason why it wouldn't be useful for things like deep learning. Yeah.
The question here, from the processor family's point of view, it used to be a kind of a waterfall model. I mean, the server side. I mean, but a gigantic
Yeah.
thing there, and then try to do the subtraction
Yeah.
I mean, will that still be the practice?
Partially, I think so. I think Amir kind of alluded to it earlier, is that we're seeing the computation aspect of this classically fall into a client-server kind of environment, which makes a lot of sense. But it's also the case that newer networks like reinforcement learning and recurrence of latent data learning and so forth, all of those techniques suggest that more of that type of training needs to be done more locally rather than in the cloud. So it's very likely that we'll see that. I think we're already starting to see it on certain types of platforms, but it's more likely going to happen because of the fact that the time value of a trained network declines precipitously over time as new data becomes available. Yeah.
Thank you.
Yeah.
So data centers are now requiring megawatts of power,
Yep.
and the primary place to achieve greater efficiency, power efficiency, is in the processor, GPU, memory interface.
Yep.
What do you see as the primary method to getting to significantly lower processor performance cost
Yeah.
per watt
Yeah.
lowest? What's the main way that we're going to get to much lower powered requirement per operation?
It's a huge problem, and we have lots of people looking at it. But the primary thing that will ultimately drive this is the ability to figure out training algorithms that don't require FP32. FP32, while it's great, and we have lots of ways in which we can program and generate all sorts of really interesting results at high enough precision. Doesn't have to be HPC precision, but it's high enough. There's a price to pay for that, and the ability of us to generate algorithms that can achieve at least as good results that we currently have using much more efficient arithmetic is the path to get that lower power. Yeah.
Between the host processor and the accelerator, what is the best methodology to get least latency and higher bandwidth?
So in training, the latency problem is not as acute as it is for inference. And more importantly, because of the way we have memory allocated among GPUs, particularly those that are connected locally, the reliance on the CPU memory is actually minimized as well. However, it is the case that some of these large networks do require a fair amount of sharing of data across the nodes, not so much to the CPU, but certainly across the nodes. And that's a big challenge, and there's a lot of work, very good work being done to sort of recast what those messages need to look like. I mean, MPI is a great starting point, but there are many ways now in which these models are being created that minimizes the amount of sharing that's needed, particularly during training and stochastic gradient descent. Yeah.
Thank you.
Yep.
Please.
Okay. So doing research like performance analysis and so on in these systems is pretty complicated. There's so many languages.
Yeah.
Lua, Python, C++, CUDA, OpenCL. You have MPI. You have clusters, and so it seems like tools like navigators, debuggers, profilers, things that tell you where the bottlenecks are pretty important. Tell us a little bit about AMD's strategy to help researchers in that arena?
Yeah, so it's a great question because it not only applies to external researchers, but even internally. I mean, we face that challenge. I can say that, we are rolling out these tools, kind of as a dribble. Some of them are coming out faster than others, but over time, you'll start to see it. But I will tell you one anecdote, which is, as we're trying to figure out ways to institutionalize the method by which we can map some of these tensors into our arrays, one of the guys who's really brilliant at all of this decided to use deep learning. So we're actually using deep learning to figure out this stuff. Yeah.
And does AMD go fairly low in describing the architecture of the processor so that you could even look at assembler code? Or?
Oh, sure. Yeah. I mean, yeah, all of that stuff. And so ROCm is open architecture. You can go read all of the documents that apply to the microarchitecture and so forth. Yeah. Right. Now, be prepared. I mean, it's not. Careful what you ask for. I mean, you might.
Yeah, I have a question about the AMD libraries for the AI in terms of the models and also in terms of the tools. I mean, the development tools,
Right.
for example, for the optimizations,
Right.
tunings,
Yep.
and the libraries could be activation functions
Yep.
and could be different models.
Mm-hmm.
Yeah, what's the
What's
status?
what's the status?
Mm-hmm.
So the path we're taking is that if you have a model in a framework, say TensorFlow, whether it's GoogleNet or VGG, it doesn't really matter. That will run no matter what. I mean, you'll be able to run that. But if you're looking for real optimized performance, the idea is that we have a layer of libraries underneath that, which are very specific about tying the model primitives to the underlying hardware. And it's that matching middleware which is actually the secret to getting high performance. And so it's not just the primitives, but it's tying them all together. I mean, it's an end-to-end type of thing, because you do have the situation, and in fact, there's some benchmarks that actually can prove this, where you can get really good results on individual primitives like 3x3 convolutions, but when you tie them all together in a great big model, it doesn't give you what you predicted to be the case. In other words, you don't multiply out by how many cases of the convolution you have in order to reach the expected performance. And that's because of the overhead of flipping in and out of the different contexts. Yeah.
Good, thank you.
Maybe the final question.
Hello, thank you for the presentation. My question is, back in maybe 15, 20 years ago, the chip producers, the objective function was maybe make the chip faster, maybe use low kilowatts per operation. I mean, my understanding was that was the purpose, just make it cheaper, faster, and with the machine learning, how much does the machine learning change the objective function? Is it still the same, or
you're talking about the error function in
the hardware, the chip itself?
Oh, the hardware. I think it depends. Certainly, we're able to, and several of the other companies involved in this are able to take fairly standard compute elements and collections of stuff and make them work. I mean, there's no problem. However, as we've already seen now, with the last two talks, that there is room for specialization. There is room for optimization, providing you know what the algorithm is. And the trick here is to find a balance between the amount of optimization you're willing to do and the risk that you're taking that algorithm is actually going to be relevant in 2 or 3 years. And because of the way that deep learning is evolving, there's a high probability that parts of, if not all of those algorithms, will be obsolete in several years.
So would you say like a 50% change in the direction just because of machine learning? Or 20%, 10%?
I'm not sure I'd put a percentage on it. A good chunk. I mean, but like I said, what we're gambling on is that the very lowest level primitives, matrix multiply, sparse matrix algebra, things that we know historically have been, sort of the baseline for all of these types of calculations, those will be immutable, right?
So let's thank Alan one more time. Thank you very much for long day of work and symposium, so see you tomorrow again. Alan, thank you very much for making the time.
Yeah, no problem. Yeah.